A camera the size of a small car just captured 3.2 billion pixels in a single instant. One exposure wide enough to swallow 40 full moons. A dataset so massive, it will take human lifetimes to fully decode. And on its very first night, this machine revealed structures in the sky that we did not even know existed. Long before a single photo was released, Rubin was already a legend waiting to be born. It sits on the summit of Cerro Pachan in the Chilean Andes, one of the driest, darkest, most stable patches of air anywhere on the planet. Almost no rain, almost no clouds, almost no light pollution. The kind of place where the sky reveals itself completely. At its heart is the Simoniai Survey Telescope, and right away it breaks the rules. Most telescopes use 2 mirrors. Rubin uses 3. That extra mirror gives it razor sharpness across an enormous field of view. The primary mirror alone stretches 8.4 meters across, which is about 27.6 feet, roughly the width of a 2-story house. But the mirror is not even the most impressive part. Bolted to this telescope is the largest digital camera ever built for astronomy. It weighs nearly 3 tons, it is about 10 feet long, and it captures ultraviolet, visible, and near-infrared light with staggering precision. Then there is the scale. A single Rubin image covers about 10 square degrees of sky, an area equal to roughly 45 full moons lined up side by side. In one snap-a-chit, Rubin sees what would take Hubble thousands of separate images to piece together. And because it sweeps the entire southern sky every 3 days, it does not just give us still portraits. It builds a time-lapse of the universe itself, exposing the flashes, the pulses, the collisions, and the slow transformations happening all around us. This is not a telescope built to look at one thing. It is a telescope built to look at everything. When Rubin finally captured its first images in June 2025, astronomers expected something good. They were not prepared for what actually came through. After just over 10 hours of test observations, Rubin produced a mosaic that scientists quickly nicknamed the Cosmic Treasure Chest. It is a 25 square degree portrait of the southern region of the Virgo cluster, the closest large gathering of galaxies to our own Milky Way, sitting about 55 million light-years away. This single image was stitched together from 1,185 separate exposures, taken over 7 nights, and inside it are nearly 10 million galaxies. Let that sink in. 10 million galaxies in one picture. Elegant spirals, ghostly ellipticals, chaotic mergers caught mid-collision. Each faint smudge is not a star. It is an entire island universe holding billions of stars of its own. To put the scale in perspective, this image spans an area nearly 70 times larger than the full moon. To display it at full resolution, you would need hundreds of 4K ultra-high-definition television screens lined up together. And here is the truly humbling part. This overwhelming sea of galaxies represents just 0.805% of what Rubin will eventually observe. Over its full mission, this observatory is expected to catalog around 20 billion galaxies. The Cosmic Treasure Chest is not the movie, it is the trailer. 10 million galaxies in a single image. Does seeing the sheer, overwhelming scale of the universe make you feel incredibly small, or strangely connected to it all? Tell me how it makes you feel down below. When you zoom into this mosaic, the universe starts telling its own story through color. The blue glow in the spiral galaxies comes from young, hot, newborn stars. The redder tones in the elliptical and distant galaxies come from older, cooler stars, the embers of galaxies that stopped forming new stars long ago. In a single frame, You are seeing both the youth and the old age of the cosmos. Zoom into one region and you find Messier 49, a massive elliptical galaxy, glowing soft yellow, packed with ancient stars. Nearby sits NGC 4535, a stunning spiral seen perfectly face-on, shining blue and white because it is actively giving birth to new stars right now. Move a little further and you reach Messier 61, one of the most beautiful spiral galaxies in the entire cluster. It gives us a rare bird's-eye view of what our own Milky Way might look like from the outside. At its center sits a supermassive black hole, about 5 million times the mass of our Sun. And M61 is a starburst galaxy, meaning it is forming new stars at a furious pace, its arms blazing with the light of young suns. But then you reach something far more violent, a triple galaxy merger. 3 entire galaxies caught in the middle of a slow-motion cosmic collision. Their shapes stretched and twisted by each other's gravity. Stars and gas are being ripped into long tails and bridges that span unimaginable distances. You can still see hints of their original spiral shapes, but they are being torn apart and rebuilt into something new. These collisions are not just beautiful. They ignite explosive bursts of star formation. They feed supermassive black holes, and they eventually forge entirely new kinds of galaxies. You are watching the machinery of cosmic evolution caught in the act. Galaxies and stars are not the only things buried in these images. There is something else scattered all across the frame. And once you spot it, you cannot unsee it. The picture has been photobombed by asteroids. You can see them as faint colored streaks cutting through the image, marking the paths of rocks moving through our own solar system during Rubin's long exposures. They are just passing through, but Rubin's software is smart enough to detect every one of them, and then cleanly remove them from the final stacked image so the deep view of the universe stays crisp. Here is where it gets sobering. In just over 10 hours of test observations, Rubin discovered more than 2,100 brand new asteroids, including 7 near-Earth asteroids. To understand how absurd that is, consider this. Every observatory on Earth and in space combined typically finds about 20,000 new asteroids in an entire year. Rubin found roughly 1/10 of the entire world's annual total in a single night, and it is just getting started. Right now, astronomers have cataloged about 1 million asteroids in our solar system. Rubin is expected to push that number to 5 million within just a few years. It will single-handedly bring our catalog of large, potentially dangerous near-Earth objects to around 70% completion. In other words, Rubin is becoming the closest thing humanity has to a planetary early warning system. A machine designed to spot the rock with our name on it, long before it ever gets close. As researchers dug through the data, they found something that should not exist. Among the new discoveries were 19 super-fast and ultra-fast spinning asteroids. But one of them shattered the rules of physics as we understand them. Its name is 2025 MN45. It measures roughly 710 meters across, which is about 2,330 feet, nearly half a mile of solid rock, and it completes a full rotation every 1.88 minutes. That sounds like a fun fact, until you understand the problem. In planetary science, there is a well-documented spin barrier. For any asteroid larger than about 150 meters, if it rotates faster than once every 2.2 hours, the centrifugal force at its equator should overpower its own gravity and tear it apart. Most mid-sized asteroids are rubble piles, loose heaps of gravel and rock held together by nothing but weak mutual gravity. They cannot survive fast spinning. They would fly apart. But 2025 MN45 is spinning once every 1.88 minutes, and it is still in one piece. For that to be possible, This object cannot be a rubble pile. It has to be a solid monolith with the cohesive strength of unbroken bedrock, around 9 megapascals of internal strength. Astronomers believe it may be a shattered fragment of a dead planet's core, a chunk of metallic or rocky shrapnel hurled out by a catastrophic collision billions of years ago and left spinning wildly through the void ever since. And it is not alone. Other ultra-fast spinners like 2025 MJ71 and 2025 MK41 suggest that durable, dense, almost indestructible debris from destroyed worlds may be far more common in the inner solar system than anyone ever imagined. Now here is one of the most haunting things Rubin did, and it did it almost by accident. There is an interstellar comet called 3I Atlas. It is only the third confirmed object ever detected entering our solar system from beyond it, following Oumuamua and Borisov. It was officially discovered on July 1, 2025. Except Rubin had already seen it 10 days earlier. On June 21, 2025, during its very first night of science validation, Rubin swept across a patch of sky and quietly captured this faint inbound comet. Its alert systems were not even fully switched on yet. But when astronomers went back and analyzed those early exposures, there it was, its fuzzy coma clearly visible, the earliest high-resolution evidence of the object's activity, recorded before the rest of the world even knew it existed. And 3I Atlas turned out to be deeply strange. It arrived on a wildly hyperbolic trajectory, moving at an excess velocity of about 58 kilometers per second relative to the Sun, which is roughly 36 miles per second. The James Webb Space Telescope found it had an extraordinarily high carbon dioxide to water ratio, a chemistry completely alien to comets born in our own solar system. Other telescopes detected cyanide gas and atomic nickel vapor boiling off its surface. Those anomalies were strange enough that some scientists, most famously Harvard's AVI Loeb, openly speculated about whether it could be artificial, an interstellar probe using our sun for a gravitational slingshot. But extensive investigation debunked that. The SETI Institute scanned it for over 7 hours and, after filtering out 74 million signals as earthly interference, found no technological transmissions. The European Space Agency calculated it was venting water vapor at a rate equivalent to about 70 Olympic swimming pools a day, exactly what you would expect from a natural, if unusual, icy nucleus. But the truth is almost more chilling than aliens. Tracing its motion reveals that 3I Atlas came from the thick disk of our galaxy, a diffused halo of ancient stars sitting above and below the main galactic plane. That means this comet is at least 7 billion years old, nearly twice as old as the Earth itself. A frozen relic from the early universe, drifting alone through the dark for billions of years before grazing our sun for a single fleeting moment. And Rubin is statistically expected to catch several of these interstellar ghosts every single year. You expect a massive star to die in a blaze of glory, a supernova bright enough to briefly outshine an entire galaxy. But Rubin's relentless gaze highlighted something far more unsettling. A colossal star that did not explode, it just disappeared. In the Andromeda Galaxy, astronomers had been tracking a star designated M31 2014 DS1. It was a monster, about 13 times the mass of our Sun, blazing with more than 93,000 times the Sun's luminosity. In 2014, it had a sudden outburst, shedding some of its outer layers. Then, over the following years, it began to fade, and fade, and fade. By 2023, deep imaging confirmed the impossible. The star was simply gone. It had dimmed by a factor of more than 10,000 without ever producing the brilliant flash of a supernova. Astronomers believe this is a failed supernova. Normally, when a massive star's core runs out of fuel, it collapses, then violently rebounds in an explosion that tears the star apart. But in this case, the rebound stalled. The shockwave did not have enough energy to escape. Instead of exploding outward, the entire star was crushed inward and collapsed directly into a black hole in complete and total silence. Think about that. A star tens of times more massive than our sun did not go out with a bang. It went out with nothing at all. It simply winked out of existence, leaving behind a newborn black hole hidden in the dark. Rubin's ability to continuously monitor millions of stars at once is exactly what we need to catch these silent deaths. Models suggest it will identify between 1.7 and 3.7 of these failed supernovae every year, finally letting us witness the quiet, terrifying deaths of the universe's most massive stars. Here is a fact that should genuinely unsettle you. Everything you can see, touch, and measure, every star, every planet, every galaxy in those images, makes up only about 5% of the universe. The other 95% is made of two things we cannot see at all: dark matter, about 27%, and dark energy, about 68%. Dark matter is the invisible scaffolding holding galaxies together. Dark energy is the mysterious force ripping the universe apart faster and faster. And one of Rubin's primary missions is to map the part we cannot see. It does this using a phenomenon called weak gravitational lensing. According to Einstein, massive objects warp the fabric of space-time, bending the path of light passing through them. As light from billions of distant galaxies travels toward Earth, it passes through invisible filaments of dark matter and gets very slightly stretched and distorted by tiny fractions of a degree. That distortion is far too small to measure on any single galaxy, but Rubin can catalog the precise shapes of billions of galaxies across the entire southern sky. By statistically analyzing all of them together, it can reverse engineer a three-dimensional map of the invisible dark matter holding the universe together, revealing structures hundreds of millions of light-years long. In other words, Rubin is about to draw us a map of the cosmic skeleton, the hidden architecture that everything else is hanging on. Everything we can see makes up just 5% of the universe. What do you honestly think is hiding in the other 95%? Drop your wildest dark matter and dark energy theories down below. Closer to home, Rubin is the ultimate weapon in one of the greatest unsolved mysteries in our own solar system. Is there a hidden ninth planet lurking far beyond Neptune? For over a decade, astronomers have noticed that a cluster of icy bodies in the distant outer solar system have strangely aligned orbits. Mathematical models from Caltech suggest the odds of that alignment happening by pure chance are less than 0.07%. The most likely explanation is that something massive and unseen is shepherding them with its gravity. This theorized world, Planet 9, is believed to be a super-Earth, about 5 to 10 times the mass of our planet, orbiting so far out that a single trip around the Sun would take 10,000 to 20,000 years. It reflects almost no sunlight, which is exactly why every previous survey has failed to find it. It is hiding right at the edge of what we can detect. But Rubin's ability to scan the entire southern sky every 3 days, down to incredible depths, is tailor-made to hunt exactly this kind of faint, slow-moving object. The same machine learning filters that found the ultra-fast spinning asteroids are now being aimed at the outer solar system, searching for the agonizingly slow drift of a deep space giant. Experts give Rubin a 70 to 80% chance of finding Planet 9 within the first 2 years of its main mission. And even if it never directly photographs it, Rubin will discover thousands of new distant objects that will box in exactly where the planet must be. We may be just a couple of years away from adding a new planet to our solar system. So this raises the obvious question: what can a telescope sitting on the ground do that a $10 billion machine like James Webb cannot? The answer is not about resolution. It is about philosophy. Hubble and Webb are like microscopes. They stare deeply at one tiny patch of sky. Hubble's field of view captures about 1% of the moon's surface area in a single image. They are designed to zoom in on individual objects with incredible precision. Rubin is the opposite. It is a panoramic fire hose. A single Rubin image covers an area equal to 40 full moons, around 4,000 times the area Hubble can capture at once. Webb shows you a window. Rubin shows you the entire landscape around it. But the real difference is time. For centuries, astronomy has been about still photographs, freezing the universe in a single frozen moment. The problem is, the universe is never frozen. Stars explode, asteroids drift, black holes flare, galaxies collide. Rubin is the first telescope truly built to capture that motion. Every 3 nights, it rescans the whole sky. Then it compares each new image to a stacked template of what that patch normally looks like, pixel by pixel. Anything that has not changed disappears. What remains are only the things that moved, brightened, dimmed, or appeared out of nowhere. This technique is called difference imaging, and it is how Rubin will detect around 10 million changing objects every single night. It is, in effect, a dash cam for the entire universe, one that never stops recording. All of this creates a flood of information unlike anything in scientific history. Rubin generates about 20 terabytes of raw data every single night. Over its 10-year mission, it will take more than 5 million exposures, adding up to roughly 60 petabytes, eventually growing toward 500 petabytes of processed data. To put that in perspective, Hubble collects about 8 terabytes of data per year. The more advanced James Webb gathers around 200 terabytes a year. Rubin produces more than twice Hubble's entire annual output in a single night. Because the telescope is in Chile and the data center is in the United States, engineers built a dedicated high-speed fiber connection to beam the data thousands of miles in real time. From there, it enters an automated pipeline that calibrates images, hunts for moving objects, and flags transient events before a human scientist even looks at it. Rubin is not just a telescope. It is the first observatory truly built for the age of big data, a living, breathing digital model of the universe that updates itself every 3 days. So let us step back and look at what we have actually seen here. We started with a camera the size of a car, capturing 3.2 billion pixels at once. We watched it pull back the curtain on 10 million galaxies in a single image, including spirals being born and entire galaxies being torn apart in slow-motion collisions. We saw it discover more asteroids in 10 hours than the rest of the world finds in weeks, including a half-mile-wide monolith spinning so fast it should not exist. We watched it catch an ancient interstellar ghost 7 billion years old, 10 days before anyone else even knew it was there. We saw a star vanish into a black hole in complete silence, and we learned it is now hunting for invisible dark matter and a hidden ninth planet in our own solar system. And here is the part that should truly stop you. Everything you just saw came from barely 10 hours of test observations. The real 10-year mission has not even begun. For all of human history, we have looked at the night sky like a quiet, frozen painting. Rubin just proved that it was never frozen at all. The sky is alive. It is violent. It is constantly moving, exploding, colliding, and transforming. And for the first time, we have built a machine capable of watching it happen in real time. This single observatory is expected to teach us more about the universe in the next 10 years than we have learned in the last 50. The era of static astronomy is over. The era of cinematic astronomy has just begun. So here is my question for you. Of everything Rubin captured, the vanishing star, The impossible spinning monolith, the ancient interstellar visitor, or the hunt for Planet 9? Which one unsettles you the most? Drop your answer in the comments. I read every single one. If this rewired how you think about the sky above you, do me a favor and subscribe, because Rubin is going to send back discoveries for the next decade, and you do not want to miss the moment it finds something that genuinely changes everything. The next image this telescope sends back might not just change astronomy. It might change the world. I will see you in the next one.